chemical reactions are of immense significance as they are essential for our existence. In fact, the functioning of our bodies relies on countless chemical reactions occurring every second. Without these reactions, life as we know it would not be possible, and even the universe itself wouldn't exist. So, what exactly are chemical reactions? They occur when bonds between atoms or molecules are either formed or broken. Let's focus on a fundamental chemical reaction that illustrates this concept. It involves the formation of water. A reaction is that crucial for our survival. On the left-hand side, we have the reactants, which are the molecules that will undergo the reaction. Then, we observe an arrow that represents the transition to the product. Let's use a different color to highlight the arrow that represents the transformation leading to the product or products. Now, let's identify the reactants in the specific example. We have molecular hydrogen, H2, and molecular oxygen, O2. It's important to note that when we refer to molecular hydrogen, we are indicating that hydrogen exists in a molecular state, typically consisting of two hydrogen atoms bound together. As you can see here, there are two hydrogen atoms in this molecule. In order for this reaction to occur, we actually need two molecules of molecular hydrogen, which amounts to a total of 4 hydrogen atoms. So, to make this distinction clear, the notation H2 represents 2 molecules of molecular hydrogen, and the subscript 2 indicates that there are 2 hydrogen atoms in each molecule. Next, let's focus on the coefficient placed in front of the reactants and products. The large white 2 indicates that we require 2 molecules of molecular hydrogen for this reaction to occur, corresponding to a total of 4 hydrogen atoms. Similarly, for every molecule of molecular oxygen, which consists of 2 oxygen atoms, we need 2 of these molecules. Under the appropriate conditions, with the addition of a small amount of energy, these reactive substances, molecular hydrogen and molecular oxygen, will combine. In fact, their reactivity is so significant that they are commonly used as rocket fuel. As a result of this reaction, 2 molecules of water are produced, as depicted here. Importantly, no atoms were created or destroyed during this process. Initially, there was 1 oxygen atom present within the oxygen molecule, and now we have the second oxygen atom separated in a different molecule. Additionally, we started with a total of 4 hydrogen atoms. Now let's count the number of hydrogen atoms after the reaction. We have 1, 2, 3, 4 hydrogens. Just like that, this reaction releases a significant amount of energy, and I'm using approximate terms here, some energy and then a substantial amount of energy. When it comes to this reaction, all it needs is a small initial input of energy, and it becomes highly exothermic, meaning it releases a large amount of energy. This reaction is energetically favorable and spontaneous. You might wonder how this reaction takes place. Is it an organized and coordinated process? The answer is no. Chemistry is a highly dynamic and chaotic field. The molecules are in constant motion, bouncing around and possessing energy. When additional energy is provided, they move even more vigorously, resulting in collisions that break the existing bonds and enable the formation of new bonds. When observing these reactions in biology or chemistry class, it is important to remember that they may appear neat and organized, but in reality, the system is filled with molecules bouncing around in various unpredictable ways. This is why energy plays a crucial role. By playing more energy to the system, molecules will bounce around and interact with each other more frequently. The greater the number of reactants present, the higher chances of collision and potential reactions. Now, let's introduce another important term frequently used in chemistry: water. In this case, we have 2 water molecules. We can refer to them as molecules since they consist of multiple atoms bound together. However, since water is composed of 2 different elements, we can also call it a compound. So water can be described as either a molecule or a compound. On the other hand, molecular hydrogen and molecular oxygen, although they are molecules, are not considered compounds. To grasp the magnitude of energy produced by this reaction, let me share an image with you. You see the space shuttle and that large tank depicted there? Well, that tank contains a substantial amount of liquid oxygen and hydrogen, combining these 2 substances with a small amount of energy. An enormous amount of energy is generated, propelling the rocket, such as the space shuttle, to achieve the necessary velocity. It's worth mentioning that the space shuttle program has been discontinued, but during its operation, this reaction played a critical role. Now let's delve into the concept. This reaction overwhelmingly proceeds towards the formation of water. While it is technically possible for the reaction to occur in the reverse direction, it is exceptionally difficult for it to do so. As a result, we generally classify this reaction as irreversible, despite its theoretical reversibility. When we say a reaction is irreversible, it doesn't mean it's absolutely impossible to go in the opposite direction. It simply means that the chances of the reaction occurring in the reversible direction are highly unlikely without the input of a significant amount of energy. To reverse this particular reaction and convert water black into its constituent elements, a process called electrolysis is required, which involves supplying energy to the system. However, the way the reaction is presented with an arrow pointing in one direction indicates that it is considered irreversible. Now let's turn our attention to reversible reactions. I have an example of a reversible reaction here. We have a bicarbonate ion, which is a molecule or atom with an imbalance of electrons or protons, resulting in a net charge. In this case, we have a hydrogen ion and a bicarbonate ion. Both of these ions carry charges, with one being positive and the other being negative. In this reaction, we have the bicarbonate ion and the hydrogen ion, which is essentially a hydrogen atom that has lost its electron, sometimes referred to as proton. These two ions participate in an equilibrium reaction, which means it can form carbonic acid. The process involves the hydrogen ion attaching to one of the oxygens in the bicarbonate ion. Equilibrium reactions occur when the reaction can go back and forth between the reactants and products in an actual solution. If you add more reactants, the reaction will tend to favor the formation of more products. On the other hand, if you increase the concentration of products, the reaction will tend to shift towards the formation of more reactants. In a real system, the reaction is constantly oscillating between the two sides. The different reversible reactions may favor one side more than the other. The presence of higher concentrations of one side of the reaction can influence the equilibrium position. If there is an increase in the concentration of one side, it may favor the other direction as the molecules or ions become more likely to interact or dissociate with their surroundings. Conversely, an increase in the concentration of the other side may shift the equilibrium in that direction as the molecules or ions are more likely to react or associate with their surroundings. Now, let's delve into the significance of carbonic acid, which is not just a random term I wrote here. Carbonic acid is a highly important compound composed of two or more elements in living systems, the environment, and even in everyday activities like consuming fast food. When you drink carbonated beverages such as sodas, they contain carbonic acid that dissociates into carbon dioxide, resulting in a visible bubbling effect. Carbonic acid plays a crucial role in how your body regulates excess carbon dioxide in the bloodstream. Additionally, carbonic acid is involved in the process of oceans absorbing carbon dioxide from the atmosphere, which has environmental implications. When you engage in the study of chemistry, particularly in the context of biology, it's essential to recognize that these concepts aren't just abstract and purely academic. They have direct implications for your everyday life, your body, and the environment in which you live. The understanding of chemical reactions, compounds, and equilibrium reactions allows us to comprehend the underlying processes that govern various aspects of our existence. Grasping these concepts, we gain insights into how your bodies function, how substances interact with one another, and how chemical reactions impact the environment. Therefore, studying chemistry goes beyond mere intellectual curiosity, as it has practical applications that affect our well-being and the world around us.